Okay, this is probably going to be the last topic I cover this semester, and really this will be the heart of what we wind up doing for the rest of the semester. Um, and we're going to take. So, all right, we spent the last few lectures learning about the general case where we have three-dimensional motion, and it's probably a bit much. All right, so the majority of the problems we're going to solve now are going to involve simplification that all of the motion is going to take place in the plane. All right. Now, what does that mean? That means um, uh, any motion, if we're talking about the xy plane, any velocity in the z direction is equal to 0, as well as any rotation in the x or y directions is 0. So that leads to a simplification for the equations of motion. Namely, the sum of the forces in the x are going to be equal to, like, say, the mass of the object times the acceleration of the um, center of mass in the x. Now, because vz equals 0, the acceleration in z is also going to be equal to 0. So we get that simplification. And then all rotation has to take place in the plane as well. So, like, that only makes sense, right? If I have an object, so z is coming out of the, say I have an object made up of 2 points connected with a bar or something like that, and all of the velocities have to take place in the xy plane, then there can be no rotation in the x or the y because they both involve velocities in the z. So here, the only one that's left will be omega z. Okay, so I'll show you kind of exactly where these That's x. All right, so what we have here are really three equations of motion, and then sort of two equations, or I'm sorry, three equations result in motion of the object, and three equations result in a like an equilibrium situation. Now, it doesn't mean you can't have forces in the z. It's just that they have to balance out to zero. It's likewise for the moments in x and y. More often than not, we ignore them completely. And so that's kind of the gist. And so we'll just use these three equations to solve problems instead of the more general situation that we just went over. Now, I guess, what follows from that is also the terms for the kinetic energy. There's a translational part and a rotational part. So the so this is actually the same equation, right, that we just covered, except this is the scalar inertia, because n is always going to wind up being equal to k, the z component of all. So the axis of rotation must reside, must be coming out of the plane. So if n is k, then and if the coordinate, if this is basically just that IZZ, as long as the z the z component of the ZZ component of the inertial tensor is or like the principal axes. If the z principal axis is aligned with the z inertial axis, okay, that's where the ZZ comes from. But this is probably probably a more correct way of putting it. Okay, because it doesn't necessarily have to be that the inertial this doesn't have to necessarily be the principal axis, but this is, that's probably the more correct statement right there. So, and then nothing else really needs any sort of nothing else really. I don't think anything else is going to wind up needing any more clarification. So those are our four equations. Everything else just follows directly. Nothing else is changing. All right, so we're going to solve a bunch of problems where all the motion is constrained to reside in the plane, and that's kind of where, like, your the majority of what you're going to be responsible for comes from. Or, we're going to be solving a bunch of planar problems, really.